Hello, good afternoon, everyone. Thank you for being on time. We're going to go ahead and get started right away. We're going to spend the first maybe 10 minutes wrapping up lecture one, and then we're going to go ahead and start on lecture number two. So we spent quite a bit of time last week talking about how to set up an experiment and how to collect good data. For example, you have to have a large sample size in each group, and you have to have the proper control as well as know how to standardize your variables, right? To keep everything the same between the control group and the treated group. And so you're only comparing one thing at a time. But it's important to understand even when you do experiment that way, sometimes the trends that we've identified might not have a direct effect between the independent and the dependent variable. Sometimes two things seems to have a relationship, but not necessarily one thing causing the other. We call those things correlations, okay? A correlation between two variables just means that they appear to show the same trend. For example, if one goes up, the other also goes up. But again, correlation does not necessarily mean there is a cause and effect relationship, okay? So in this picture, we can see that there is a correlation between psychological stress, how stressed a person is, compared to how likely the person is going to catch a cold, okay? Based on this graph, it appears that the more stressed out a person is, the more likely the person is going to catch a cold. Does that mean stress is responsible for causing colds? Not necessarily. If we take a deeper look, we know that there are many underlying causes for a person to feel stressed out. Maybe they have other illnesses. Maybe it's poor diet. They don't exercise enough. They don't have enough sleep. All these things can result in high stress. And at the same time, all these things can also increase your risk of catching a cold. Okay? So just because two things are related doesn't mean, just because A is related to B does not mean A causes B. Okay? There could be other unknown factors, C, D, E, F, that results in both A and B. So that's why we have to be careful when we look at data. Okay, we don't automatically assume it's a direct cause. There is a website that you can check out if you are interested in. It shows you random things that have very strong correlation between each other. Okay, so apparently there is a correlation between how much cheese is being consumed versus the chance of being tangled and die, by your bed sheets. Okay, so you can see the two lines almost overlap each other perfectly, but common sense would tell you there is absolutely no correlation between the two things. No cause and effect between the two things, even though it seems like there is a correlation, right? So there's a link here, and you can check out all sorts of bizarre things that are related to each other, if you're interested. So, on the internet.
Question.
Yes, please go ahead.
Is everything in the content section?
Is everything in the content section? You mean on eCentennial?
Yeah.
Yeah. Everything is there. So if you go to here, I'll show you very quickly. This is the same note as last class though. Okay, so if you go to eCentennial content lecture, and then we're doing lecture one right now.
Oh, okay. We are still on lecture one.
That's right. We're at the end of the lecture one. Yeah, we will start too soon. Okay.
Okay. Thank you.
Yeah, no worries. What was it saying? Right. So like on the internet, right, we see a lot of these headlines, right? When we're scrolling through our phone, we see these headlines that are trying to bait us into clicking them, right? We call them clickbaits, and they often have some kind of claim that draws your attention. For example, drinking more coffee might reverse liver damage from booze. Okay, so you look at that and you're like, okay, this sounds interesting, and then people believe these things very easily. Okay, without critically analyzing the information that they're reading. Okay, so there are conflicting results, right? Like in another one, it says coffee consumption in either parents might raise miscarriage risk, right? So all these things, I want to point out that most of the case is just correlation, okay? Uh, it doesn't mean the coffee is directly responsible for reversing the effect of liver damage. Okay, maybe these people do something else as well. Okay, that has a role in making the liver more resilient to the alcohol effect, right? Like we don't know, right? See, another one here is coffee consumption may help prevent colon cancer, and then people who drink coffee read into that. It's like, oh, okay, yeah, it justify my coffee consumption. Now, people who don't drink coffee, on the other hand, would look into this headline over here and say, oh, I told you shouldn't have drink coffee, right? So there are these what we call a conformational bias. People tend to read things that aligns with their own habits, okay, and then it kind of reinforces their belief, right? Okay, but my point is, when you see these headlines, right, you should dig deeper into it, and also realize not everything is done in sound science. For example, like take this one for example. Um, who is funding the study, right? Like maybe it's, I'm just making this up, okay? Maybe it's LCBO, right? Maybe they joined with Starbucks or something. Hey, let's roll out these studies, right? So people can enjoy their alcohol and they will buy more coffee, right? My point is, sometimes some studies are funded by organizations or entities that have an invested interest in the outcome, right? And the thing about funding a particular research is sometimes you can sway the result one way or the other. It's not good science, but then it happens. Okay? So when it comes to evaluating resources, you want to be able to distinguish where it comes from, right? Like, is it a primary source or is it a secondary source? Primary sources are the original documents, the original research. These are told by the person who have conducted the research. Okay, so often these are academic research printed in peer-reviewed journals. Peer review means other experts in the field will take a look at your work and they will criticize it, they will scrutinize it and make sure that they are done to a particular standard. Right? So these are usually more reliable. Okay, but like I said, there are extreme cases where there's conflict of interest and then the results are kind of skewed. So don't believe everything you read. Always take a look at it with a critical mind. Other examples of primary sources: interviews, reporting live at a scene, like on TV, right? It's the person's first-hand account of what's going on, right? Diary, fiction, these are all primary sources. Secondary sources include things that are summarizing other people's work or interpreting primary sources. So that includes things like encyclopedia, textbooks, magazine articles, even biographies, right? Yeah, so when we look at the secondary sources, we have to understand there might be some biases in some cases, depending on even news outlet, right? Okay, some news outlets are more conservative based and others are more liberal based, right? And then the way that they report certain things might be skewed one way or the other. Okay. Anyway, my point is just that when you do your research for other courses, like your general education course, your GNET courses, right? Make sure you choose the sources wisely. And using what you've learned in this lecture, you're able to judge whether the data from any kind of science sources is collected in a way that aligns with good science, right? So things like sample size, control, so on and so forth. And that's it for lecture 1. All right. So does anybody have any question so far? All right. Now we're going to move on to today's lesson, which is lecture 2. Okay, now this is a very long lecture. Okay, if you look at the slides, it has like 101 slides. We're probably not going to be able to finish it this week, maybe. But you know, we try to pace ourselves and do as much as we can. But it's very important for you to you know, stop and ask questions along the way if something jumps out to you that doesn't make sense. This lecture is about macromolecules. Okay, macromolecules. To learn about macromolecules, I have to teach you a little bit of chemistry first. Okay, some of the stuff might be overlapping with what you are already learning in chemistry, but you know, it's a good refresher to make sure that we are all on the same page before moving on to the biology stuff. So, matter. You hear this word a lot in chemistry. Okay? Matter is anything that takes up space. That means it has a volume, okay? And it has mass, right? So together, space and mass, that's what make up matter, right? So the calculator is made up of matter. You are made up of matter, right? Air is made up of matter. It takes up space, right? It fills up the room. We don't really feel its weight, right? But there are all these pressure pushing down on us, right? That's basically the collective weight of all the gases that are above you. Matter can exist as solid, liquid, or gas. And they could change from one state to the other depending on how much energy it possesses. And the more heat you add to a solid, it might turn into a liquid and then to a gas. We are familiar with this process, you know, with water. We have ice cubes that would melt, and if you keep on heating it, it would evaporate, right? So all matter is composed of elements. Okay? Elements are substances. Substances just means like things, okay? Things that cannot be broken down into other substances. Okay, so like take oxygen, for example. Oxygen. Oxygen is an element. It's not made up of other stuff. Okay, oxygen is the simplest unit. Okay, you cannot break an oxygen and get two different things. Okay, unlike water. Okay, what's the chemical formula for water again? Anybody remember?
H2O.
Yeah, H2O, right? This is water. Water. Water, you can break it down further. You can do this at home. You can connect or you can just throw a battery into water, and then the current is gonna split the water back into hydrogen and oxygen. Water is not an element because it can further be broken down into other stuff, hydrogen and oxygen. Oxygen is an element because you cannot break it down further. All right? So, what makes up elements? Right? The smallest unit of an element is an atom. Okay, so even though you cannot break down oxygen, but what makes up, like if you have a flask of oxygen, right? Like what makes up those oxygen? Those will be the oxygen atoms. Okay, is the smallest unit of an element that has the same properties as the element itself. So every single oxygen atom, they have the same chemical property and the same physical property as each other. Okay. And if you look within the atom, all the atoms are made up of three things. It's made up of protons, neutrons,
and
and electrons. That's right. Okay. So you might have learned this before. You might have learned this in chemistry already. Have you guys learned this in chemistry yet? Like last week? Just curious.
yes.
Yes?
Yeah.
All right,
Yeah.
so I'm not going to spend too much time on it, okay? Protons and neutrons are in the center. It forms the nucleus. And then the electrons are going to be like, flying around. Okay, so protons P for positive, okay? And then electrons are negative. No charge for neutrons. Now, all the elements that makes up the universe can be found on the periodic table. And this is the periodic table. Okay? Some of them are discovered in nature. Other ones are made in the lab. Okay? So, but everything that we know in this universe, everything that exists in this universe is made up of these elements. Okay? Combinations of these elements. Again, to make water, we need oxygen and hydrogen. We put them together, right? So that's the periodic table. You'll use it in chemistry, not so much in biology. Okay? But I want you to know, if you can see it on the periodic table, then it is an element. Okay? For example, you can see C right here. What does C stand for? Does anybody know?
Carbon.
Carbon, that's right. So carbon is an element, right? I do not see water on the periodic table. Water is not an element. Okay? Even though there are so many different elements on the periodic table, or 118 on this one, there are only 5 elements that makes up over 96% of the human body. Okay? They are the following: carbon, nitrogen, oxygen, hydrogen, and phosphorus. Okay. Carbon, you probably, have some around in your home. Okay. Like, the tip of the pencil, right? That's carbon. It's made up of graphite, which is carbon. I know people call them lead. At one point, maybe they were lead long time ago, but lead is poisonous. Okay. So it's not lead. It's graphite. It's carbon. Okay. Some of you might be wearing something expensive that is made up of pure carbon on your hand. Anybody know what I'm talking about?
Diamond.
That's right. Diamond is pure carbon. Okay. Nitrogen. Nitrogen is in the air. Okay. 70% of the air that we breathe is nitrogen. We cannot use it directly from the air though. Okay. So we have to consume it from our food. Oxygen, 20% of the air that we breathe is oxygen. Okay. Hydrogen, they make things like in balloons, right? It used to be hydrogen balloon, but then hydrogen is very, very flammable. It's not safe for kids to play with hydrogen balloons, so they change it to helium. All right. And phosphorus, anybody know where you can find phosphorus?
Brain.
In the what? In the brain?
Yeah.
No, I mean like household items. Right? Any household items that you might be able to find some phosphorus? Maybe in the kitchen. Anybody know what I'm talking about?
Matchstick.
Matches, that's right. Okay, the match. It's on the strip, not the head. So you strike it, it makes fire. Okay, so these are the key elements that makes up over 96% of the human body. And then we have what's called trace element. Okay, trace elements are elements that are only required in small amount. Okay, you don't need too much of it. In fact, if you have too much, if you have an overdose, it will lead to some kind of disease condition. Not having enough is also a problem. So you just need to have the right amount. Okay. Example of trace elements include things like zinc, which is important for your defense system. Of course, you know about calcium, which you need for the bones. Right? And you also actually need it for muscle contraction. Right, to move your muscle, right, to move around, you need calcium. Iodine, okay, iodine is important for making hormones. And I'll show you what happens if you don't have enough on the next slide. Magnesium, also needed for muscle contraction. And you can buy almost any trace elements at Walmart or like Shoppers Drug Mart or Costco or wherever you get your stuff, right? The Jameson is a big company that makes all these supplements. So you want some extra magnesium, no problem, right? You can just pop a pill. Okay, so they even have these multivitamin, right? Multiple things in one pill, and then you consume. Right? But most people don't need extra intake of these things. Okay, if you have a well-balanced diet, usually you're okay. Right? But some people, maybe there is some genetic condition that they have. They don't have enough iron, for example. They cannot absorb iron from the food. Right? Then that's when they have to take supplements to help them. Right? Calcium is a common one, right? For bones, right? To make them strong. Okay? So everybody understand? We have the key elements: the carbon, hydrogen, oxygen, nitrogen, and phosphorus. And then we have the trace elements, things that you only need a little bit of. Anybody want to give me another example? You can type in the chat or, shout it out if you have other examples of trace element. No? No, nobody takes anything here.
Iron.
Yeah, iron, right? We talk about iron. We need iron for our blood, right? To carry oxygen, right? That's a good one.
So, vitamins are included.
Vitamin is not an element though. Vitamin is like a, collection of compounds, of molecules. But yeah, some people take vitamins. No? Yeah. Anything else, guys? No? Okay. Potassium, right? That's another one. Potassium, sodium. These things we usually take just through our regular diet. Okay, but they are trace elements. We don't need a lot of them, but nevertheless, we need them. So iodine deficiency can lead to goiter. And so you have a gland here in the neck that's called the thyroid gland. Okay, that here is the thyroid gland. You learn more about it next semester, but it makes hormone for you. It helps you regulate your metabolism. It's the only gland in the body that makes that uses iodine to make hormone. So if you don't have enough iodine in your diet, it gets big. Right? Try to compensate by getting bigger, right? So it can pump out more hormone, right? Where do we get our iodine anyways? Anybody know?
Sea salt and fish.
Yeah, so from sea food in general, and the salt in Canada, they have been iodinized. Okay, they add iodine to the salt so that you don't have to worry about deficiency. All right, in places where this is not done, then people need to get their iodine from natural sources, right? Like seafood. But if you don't have enough intake of iodine, you might get goiter. Calcium deficiency can lead to osteoporosis. That's when your bone becomes very spongy and it's weak, and you can break them easily. Right? So that's deficiency in trace elements. Now, I want to show a few other related terms to you. There's something called isotopes. Right? Isotopes are atoms of the same element that have different number of neutrons. Okay. So first of all, atoms of the same element, they always have the same number of protons. For example, if I look at carbon, right, all carbon atoms are going to have 6 protons, always. If you change the number of protons, you will change the element. Okay, so let's take a look at the periodic table. The number here tells you how many protons it has. Okay, so carbon, they all have 6 protons. If you change the number of protons, if you make it more, then it becomes nitrogen. If you have one less, then it becomes boron. So protons do not change. Okay, but the number of neutrons can change. Okay, some carbons have more neutrons than others. That makes them heavier or lighter. Okay, so when we have atoms of the same element with different number of neutrons, we call them isotopes. Do you understand? Okay. So
Professor, can you please repeat? Sorry.
Sure. Atoms of the same element. Okay, so if you look at all the carbon atoms, they would have same number of protons. If we look at the number of protons in oxygen, all of the oxygen will have the same number of protons. Does that make sense, that part?
Yes, Professor.
Okay, now neutrons, which is what help makes up the atom, right? Neutrons might be different for the same element. So some carbon might have more neutrons than other carbon atoms. Okay, if you take a look at oxygen, some might have more neutrons than others. That's what isotopes are. Okay, isotopes are basically same protons but different number of neutrons. Some isotopes are unstable and they break down on its own. Okay, and these isotopes are useful for various reasons. Okay? Carbon-14 is an unstable carbon. The regular kind is called carbon-12. Okay, this carbon-14 is unstable. It breaks down. Usually when these things breaks down, they give off a little bit of radiation, and you can detect these radiations. When a person dies, the number of carbon-14 is going to slowly break down. Okay, I shouldn't say when a person dies. Okay, when a living thing dies. So it doesn't have to be a person. It could be like an animal or something. So by checking how much carbon-14 is left in the bones of some organisms remain, you can do the math to work out when the thing died. Okay, like you and I, we both have the same amount of carbon-14 when we are alive. As soon as we die, we all die with the same amount of carbon-14, but once we die, it slowly breaks down in a predictable way. So by looking at how much carbon-14 is left in the bones when it was discovered, you can work your way back to see when the person died. All right, we can do this for all living things, like, dinosaur bones and stuff like that, right? Iodine-131 is another isotope. We can use it to treat thyroid cancer. Okay, when you inject iodine-131 in the body, the only place it goes to is the thyroid gland, because that's the only place that the body uses it, right? And when it gets to the thyroid gland, because they are unstable, they will break down. When they break down, they give off radiation, which will kill the cancer cells. Okay. If you have a smoke detector at home, and you should have one, by law you should have one, it's called the Americum 241. Okay, actually it's Americium 241. And it slowly breaks down to give off a little bit of radiation, but it's not dangerous. Okay, the radiation helps with detecting the smoke. You don't have to memorize any of those. Okay, my point is that isotopes, they have different number of neutrons, and some makes it unstable, and we can use it in different ways. Okay, I just want to reiterate. Protons do not change, right? Number of protons do not change for the atom. When neutron change, we can have isotopes. Electrons can also change. Okay? Sometimes an atom can pick up electrons, other times they could lose electrons. When they gain or lose electrons, they become ions. Okay? Many ions exist in the body that are vital for our function. We call them electrolytes. Okay, so when you drink your sport drinks, there's the sugar in it, of course. But if you look at the back, there are important electrolytes like sodium, potassium, chloride. All these things are going to go into the blood, right? And it's going to be important. Diarrhea is a common cause of death in poor countries, okay? Because they don't have access to clean water, they get sick from contaminated water, and they don't have electrolytes to replenish once they lose it, and they become severely dehydrated. And that's how people can die. Right? So that's one example of why electrolytes are important. Okay. So to summarize, for example, let's take nitrogen. Okay, nitrogen. Let's go back here. I just want to emphasize this. Okay, so nitrogen. Nitrogen is made up of many nitrogen atoms, right? Many nitrogen atoms. Okay. All of them have the same number of protons. Okay. Some might have extra neutrons. And we call them isotopes. Okay. And if they have more or less electrons, then we say ions. Okay? Please let me know if you have any questions. Okay, fantastic. Moving on.
So we call them nitrogen ions.
Nitrogen ions. That's right. If they gain
Okay.
electrons or lose electrons, we say nitrogen ions.
Okay, so where do they gain or lose the electron? Like, where do they gain them from?
Yep. That would be your chemistry teacher will teach you that.
Oh, okay. Okay.
Yeah.
Okay.
Thank you. All right. So let's move on. Right. We know what atoms are now, hopefully. Right. They make up elements, right? Elements is everything on the periodic table. You cannot break them down further. But as with the example of water, we know we can take atoms and we put them together to build things, right? Okay, build more complicated things. So here is another example other than water. Okay. Sodium chloride. Right? What is sodium chloride? We can take sodium atoms, okay, which would be what makes up the sodium element. Okay, and for those of you who don't know what sodium is, this here is sodium. It's a metal. But when people think of metal, they think of something really hard, right? Like a iron bar or something. But this is also a metal. It's very soft, so soft that you can actually cut it with a knife. Okay. Now, sodium is very, very reactive with water. Okay, that's why you actually have to store it under oil so it doesn't react with the moisture in the air. And you can see in the picture, the person is wearing glove because the moisture from your hand can set off a reaction in the sodium. That much sodium in the picture, if you drop it into a tub of water, it will cause a violent explosion. Okay, you can search it up on YouTube and watch it for yourself. Okay, my point is sodium is dangerous. Okay, we don't want to keep it in our house. Okay, just can set off violent reaction when it comes in contact with water. Okay, hold your question. I think some of you might have a question about sodium. Like if it's so explosive, then why do we need sodium in the body, right? Okay, so just hold that thought. Number two, we have chloride here. Okay, chloride. Chloride is a gas and it's poisonous. Okay, they use it to make a poisonous gas in the Second World War. Also, not something that you want to keep around at home, right? However, when you put sodium and chloride together, they could react to form sodium chloride. Okay, and now it is a compound. A compound is when you take elements and you put them together, you build them together into compounds. okay? And the smallest unit of a compound is a molecule. Right? Smallest unit of an element is an atom, but smallest unit of a compound is a molecule. And sodium chloride is table salt. Okay, and as you know, table salt is very stable. It's not explosive, it's not poisonous. We add it to our food, right, to make them taste better. So it's important to understand when atoms come together to form molecules, the properties completely changes. Okay, the final product that you get no longer resembles the original stuff. Right? That's important to remember. Right? Any question? So when we say we need sodium in the body, we are not talking about the elemental form. We're not talking about a solid form. We're talking about the ion form. Okay, the one that is dissolved in water. And I'm going to show you more examples of that in a bit. But I want to show you 2 ways that we can put atoms together. Right? So here we have the sodium atom, we have the chlorine atoms. For reasons that you will learn in chemistry class, the sodium likes to give away electron. And chlorine, they like to pick up electrons. So they make a perfect match, right? Sodium wants to give it away, chlorine wants to pick one up, they could bond together. So this is what we call an ionic bond. Okay, ionic compound. Okay, and this involves a transfer of electron. Okay, that's short form for electron. A transfer of electron. In some other cases, like water, rather than transferring the electrons, again, for reasons you will learn in your chemistry class, the electrons are being shared instead. So we call these covalent compound. Right, so this is share of electron instead of transfer of electron. Okay, and the bond is basically the glue that holds them together. In an ionic compound, they form an ionic bond. In the covalent compound, they have a covalent bond. Okay.
I have a quick question. So the negative on the chloride ion, is that because it's taking the ions from the sodium, the positive?
Absolutely. Yeah, so
Okay.
very, very good observation. Once they come together, the chlorine becomes negative because of that extra electron.
Okay.
And the sodium has lost one, that's why it's positive, right? But the key
Okay.
thing to know here is one likes to give it away, the other wants to get it. That's why it's a perfect partnership, right? If both wants to give it away, then it's not a good partnership. Anything else?
Professor, excuse me.
Yeah.
Yes, Leah, go ahead.
Sodium is positive and chlorine is the negative. So always positive and negative should be together.
In ionic compound, yes, yeah, but that's not the main point here. Okay, you will learn about the positive, negative in chemistry again. The main point here is in ionic compound, there is a transfer of electron. Okay, one element gives it to the other, right? Okay, whereas in covalent, there is a sharing of electron.
What is the difference between ionic and covalent
Okay,
bond?
for us, it's only about how the electrons are being handled. Okay, if the electron is again transferred, is given from one to another, then we say it's an ionic. Okay, it's usually a metal with a non-metal. Covalent is a sharing of electron. Right? They are both using it. The oxygen did not give the electron to a hydrogen. They are sharing it together. Okay. In the ionic compound case, the sodium actually gave away the electron to chlorine. Okay, look at the picture, right? This
But
one.
chlorine, okay, chlorine cannot give to sodium.
That's right.
Okay, good.
Yeah, sodium gave to chlorine, okay? Sodium gave to chlorine.
But for a covalent bond, they can both
Share.
share.
That's
Okay,
right.
okay,
That's
good.
a key thing
Thank
I need you to know for our purpose, okay?
Okay,
Yeah,
thank you.
yeah. And again, the complicated stuff you're gonna learn in chemistry. Myriad, I think you have a question.
Yes, Professor, but you already answered the
Okay, yeah.
question. Thank you.
Okay, thank you. All right. It will get better, okay? I hope it will get better. Okay, don't get too bogged down by the details for now. We're just like having an overview of the basic chemistry so that you can understand the biology stuff. All right, exactly how do you know if it's ionic? How do you know if it's covalent? You will learn it in chemistry, okay? So next thing is about organic molecules. By definition, a molecule is organic if it contains carbon atoms, okay? If in the structure it contains carbon, we say it's organic. This has nothing to do with organic food. That's a different definition. We are talking about organic molecule. Okay, whether it is organic or not depends on whether it has carbon or not. Many organic molecules have a biological significance in it. Okay, it's important in living things like glucose and proteins. These are organic molecules, and it's important for various reasons that we will learn about. But you got to understand, not everything that's organic has to do with living things, right? We have a lot of things at home that are organic molecules. You might have heard of polyester, right? Where do we find polyester at home?
Clothes.
Yeah, in your jacket, right? Okay, did you have any water resistant coating, like a windbreaker? That is made up of polyester. Okay, if you would like to cook and you have the non-stick pan, like frying pan, the black coating, that's called Teflon. That's organic. Okay. Methane gas, like the greenhouse gas here shown here in this picture, CH4, that is organic. Why are these things organic? It just means they have carbon in them. That's all. There are a few exceptions. These are the exceptions. I don't know why, but people who came up with this thing, they're like, you know what? Let's confuse the students, okay? Everything that has carbon, we're going to call them organic, except for these three things. Okay, so CO is carbon monoxide. That is poisonous. You should have a monoxide detector at home along with your smoke detector. Carbon dioxide is something that we breathe out. Okay? And then CN is cyanide, which is also very poisonous. Okay? If I show you a question on the test and I ask you which of the following is organic, you choose everything that has a C, but then you do not choose these ones, okay? We will learn more about cyanide and carbon dioxide later on in the course. Hopefully that makes sense. All right, moving on. Taking everything we've learned so far, let's try to understand a little bit more. Water is very important for many reasons, right? We cannot survive without water, okay? For extended period of time. Okay? We can survive without food for quite some time, but without water, we would die, right? Very quickly. So what makes water an important molecule is the fact that they are polar. Okay? So I'm going to explain to you what that means. Right? What is this? This is class notes, Gen 15. Okay? I don't think we're going to write too many notes today, okay? But let's just do what we have to first. So again, you should know by now, water is H2O. Okay, water. Okay. All the water that exists in the world is H2O. Right? If someone try to sell you H3O, don't buy it. It ain't water. Okay. Now, let's draw water. And you don't have to know how I draw this. Okay, like you don't have to know how to draw the water molecule. You just what am I trying to say? I wouldn't ask you to draw it, okay? Your chemistry teacher again will teach you how to draw these things later, okay? For now, just believe me, that's what a water molecule looks like, okay? So H2 means there are 2 hydrogen atoms and then there is an oxygen atom. All right. Now this bond here, this bond that's holding the hydrogen and the oxygen together, that is called a covalent bond. Okay. And again, you don't have to know, for me, for my course, you don't have to know why it is covalent and not ionic. Okay. You just have to believe me, they are covalent. Now, earlier I was telling you the meaning of a covalent bond, right? Covalent bond means there is sharing of electron between O and H. All right. Now, you know, sometimes I buy a toy for my 2 girls, but then, you know, I would tell them, you guys have to share it, okay? I don't want you to fight over it. Make sure you share it. And they're like, okay, we'll share. Right? But the big one, like my older one, even though she's sharing the toy, I know she's the one who's playing with it more. Okay? She's still sharing, okay? But then she kind of hogs the toy and plays with it more. That's how it is with atoms as well. The oxygen and the hydrogen are sharing the electron, but like my older kid, the oxygen is hoarding the electron. It's like, okay, I'll share with the hydrogen, but you know what? I like it more. So it pulls the electron towards itself. And for that reason, the oxygen is going to be slightly negative. That's what this symbol means, okay? Slightly negative. So oxygen pulls electron towards itself. You might ask why, but again, you don't have to know why. If you really want to know, ask me during the break, okay? But it's something you will learn later on anyways in, again, chemistry.
Quick question.
Mm-hmm.
For the water,
Mm-hmm.
is it only the oxygen in the water or generally oxygen pulls electrons towards itself?
That is an excellent question. It depends on who it is sharing with, okay?
Okay.
Yeah. So yeah, that's a great question. Hydrogen, right? For that reason, because it's like, you know, not getting the electron as much, it's slightly positive. That's what this symbol is, okay? This symbol that's like an 8 but missing a little bit, that means slightly. All right? So when there is an uneven sharing of electron, we call a molecule polar. Okay? It does not mean it have extra or missing electrons. It just means the electrons are not being shared evenly. So that makes it polar. Okay. Overall, it is still neutral. Okay. Neutral means no extra electron, no missing electron. Okay. Now, let's see what happens if I put one water molecule next to another water molecule. Okay. Oxygen is slightly negative, hydrogen is slightly positive. When you put them close to each other, they are attracted to each other. So there is a little bit of attraction here. This attraction, which we will talk about multiple times in the course, so I want you to know it, is called hydrogen bond. Okay, it is attraction. We can say a type of attraction between two water molecules. Okay? They basically form little magnets. They're behaving like little magnets that are attracted to each other. If I have another one here, right, they would be attracted like this. So I want you to have a thought experiment, okay? It's like we visualize this in our head, okay? And we think about it. I have a dime here. We don't have pennies anymore, so dime is the next smallest thing. We have a dime here. And let's say you have a dropper, like an eyedropper, water dropper, like for those medicine things, and you're gonna drop water on it, okay? Onto the dime, slowly. So try to do this in your head, okay? How many drops of water do you think you can fit on the dime? Okay, let's do a poll. Okay. Right. Less than 10, 10 to 20, more than 20. Okay. A, B, C. Let's see. What do you think? How many drops of water are you able to fit on the dime? Okay, very nice. Just an educated guess. Okay, there's no right or there's a right answer, but then there's no right or wrong tries. Okay. Okay, I'm gonna leave it at that. Thank you for those who have participated. Most of you think is less than 10, 10 to 20, more than 20. I mean, it depends on the size of a dropper, but like if we talk about like a standard dropper, okay, you can easily fit 10 to 20 for certain. More than 20 is also possible if you do it slowly. Okay. Now, if you don't believe me, you can try it out. But if I draw this picture, I think you can visualize what's going on. Okay, so this is a dime. And when you drop the water actually will form a dome, right? Can you visualize this? Right, like a water dome that sits on top of the water, rather than just like falling over, right, and spilling. I mean, eventually it's gonna spill, but it's not gonna spill immediately. So how come the water can do this? How come it feels like something is pulling towards the center of the water and holding the dome shape? It's because of the hydrogen bond. Right? Because water is attracted to each other. They're going to be pulling onto other water molecules, and therefore is able to retain this dome shape. Do you understand? Okay, it's like if I asked the whole class to fit onto 2 tables in a classroom to prevent people from falling over, you got to hang on to them, right? That's what the water molecule is doing. They're hanging onto each other through these hydrogen bonds. Questions? Okay, I hope you're with me. All right. Moving on. Because water is polar, it makes it a good solvent. Okay, a solvent is usually the liquid portion of a solution. I'll just give you an example to help you understand this. Okay, you guys know Kool-Aid, right? It's like those fruit punch powder. Okay, so if you add the Kool-Aid into the water, you get the fruit punch. Okay, so this is the solute, which is the solid part. And then the solvent is the liquid portion. And when you mix them together, you get a solution. Does that make any sense? If you add salt into water and you dissolve it, the salt is the solute. Okay. So our body is made up of a lot of water, right? There are a lot of solute that are dissolved in it, right? To make us functional. All right. Now, of course, not everything can be dissolved in water, but let's talk about the ones that is dissolvable. Okay. If something can be dissolved into water, we call them hydrophilic. Okay. Hydrophilic molecules. Hydro means water. Philic means loving. These are water-loving molecules, like NaCl, okay, salt. Now, again, don't get too caught up with the positive and negative, but you already know from the previous picture, right? That's what sodium chloride looks like. Okay, it has the positive sodium because it gave the electron to chloride, right? And the negative chloride here. So when you put a chunk of salt into water, the water basically pulls apart the Na and the Cl. Here, I will draw it for you. Okay. Okay, so let's say we have the Na here. Okay. Which part of the water is going to surround the sodium? Think about it. Is it the oxygen or is it the hydrogen?
Oxygen.
That's right, because opposite attracts when it comes to charges. Right? So because the oxygen is slightly negative, you will have all the oxygen surrounding it, hugging it. Okay? And then when it comes to the chlorine, which is a little bit bigger, but because it has a negative charge, the hydrogen will be hugging it now. Okay? So if the water is able to do that to separate it, then that makes the substance able to dissolve in the water.
Mr. Vincent, so actually the water is breaking the bound.
That's right. Yeah, yes, yeah, you can think of it like that. Okay, the sodium and the chloride, they try to hang on to each other. Okay, but as soon as they go into the water separates them. Okay, it surrounds them. Okay, if you're able to do that, then you can dissolve it in water. Okay? But the key thing here is this. The key word that I want you to know is that hydrophilic. Okay, so other than salt, can someone tell me something else, maybe in your kitchen, that is hydrophilic? Don't think too hard. Just think about everyday life example.
Sugar.
Sugar is absolutely hydrophilic. Okay. Anything else? It doesn't even have to be solid. Okay. All right. What else can you mix in water and then it will dissolve?
Baking soda.
Yeah, sure. Baking soda is another one, right? Okay, maybe just one more. Any kind of liquid that you can, mix with the water and then it, like blends together. Think about cooking, huh?
Salt.
Salt? Did you say salt?
Salt.
Yeah, okay, yeah, that's right. Salt, okay, but it's right here as well. Vinegar, right? I was thinking vinegar. Okay, vinegar. That's also hydrophilic. Basically, if it dissolves in water or it mixes with water, then we say it is hydrophilic. Okay, now give me something that is not gonna mix with water.
Oil.
Oil, exactly. So oil and other things that cannot dissolve in water. Okay, usually these are non-polar molecules. Okay, we call them hydrophobic. Hydro is water. Phobic is like scare off, right? Scare off. Okay, so they're scared of water. Okay? So they will not dissolve in water, like oil. Right? That's why salad dressing, they will separate after a while. Okay. Wax is another example. Okay. You have candle, you let the wax melt and then it hits the water, it will stay floating. It will not dissolve in the water. Hydrophobic. Everybody okay with hydrophilic and hydrophobic? Great. Next, we have to learn about the pH scale briefly. The pH scale is used to describe if a solution is acidic or basic. Okay. Examples of things that are acidic would be like lemon juice, right? Things that are sour, they could be corrosive. Soft drink is acidic. You have acid in your stomach, that is acidic, right? So all these things are acidic. Less than 7 is acidic. Okay. If it's equal to 7, then it's neutral. It's not acidic, it's not basic. Pure water is neutral. Okay. The water that comes out of your tap, that's not pure. It has all sorts of stuff in it. Okay. That might not be 7 exactly. If it's greater than 7, then it's basic. Okay. Things that are basic tend to be slippery to the touch. They tend to be bitter. So things like baking soda, if you add too much baking soda in your cupcakes or whatever, it turns out bitter. You know, I don't know if people know what milk of magnesia is, but it's basically like Tums, okay? But like in liquid form. When you have a heartburn, you take these things, right? So these are basic. Okay. Human blood is slightly basic. Slightly basic. Okay. So 7 is neutral. Right? Human blood is typically between 7.35 to 7.45. So a little bit basic. Okay? You don't have to know these words, but I'm just telling you, if your blood pH is less than 7.35, less than the lower range, then it's too much acid in the blood. We say acidosis. Osis is too much of something, too much acid. If it's greater than the upper range, then we say alkalosis. Okay. Both acidosis and alkalosis are dangerous. It could cause you to die. Okay. So our respiratory system as well as our urinary system will work to keep the pH of the blood within that narrow range. Okay, because they use something called buffers. Right. That is something we will learn next semester. Right now, I just want you to understand what pH is. Okay, acidic versus basic. That's all. Okay, let's do one concept check question. Okay, anyone else before I close the poll? And again, some of these questions are gonna show up on the quiz, right? So make sure you practice on your own as well and always record the right answer during class. Most of you got it right. Okay, if you have been copying the notes, you will know that it is caused by uneven distribution of electrons. Even though the oxygen is sharing with the hydrogen, but the oxygen is like, pulling it towards itself, right? Which makes the molecule polar. And that is all for the chemistry. Whew, we're done with chemistry now. We're gonna move on to biology after the break. Okay, so please come back at 1:45. See you in a bit. Okay, let's keep going. So now that we understand the basic chemistry, let's move on to the biology stuff. Okay, and we're gonna talk about the key macromolecules that are significant in any living organisms. Okay, so let's start by looking at what the four main macromolecules are. Okay, so we wrote this down last week. Let's talk about it again. We have the carbohydrates, okay, people call them carbs, proteins, lipids, as well as nucleic acids. Okay, they are macromolecules because they are really, really big compared to something like sodium chloride, which only has two atoms, or water, H2O, which only has three atoms. These macromolecules, they have hundreds and sometimes thousands of atoms in them. So they are really, really big. Generally speaking, macromolecules are polymers. They are polymers because they are composed of many repeating monomers or subunits. Right? So if we think about carbohydrates, it's actually really, really, really long, and each of these little circles represent a subunit. The best way to think about it is like a train. The train is very long and it's made up of individual carts, right? And you can always add more carts to it to make the train even longer. So these macromolecules, they have different monomers. They have different subunits depending on which macromolecules you're looking at. And this is a summary table that shows you the different kinds of monomers. You don't have to memorize it like at this point. We're going to talk about each one of them in much more detail. And then at the end of the lecture, you will have a better idea of what you need to remember. So, how do we connect monomers together? We have a monomer here and we have a monomer here. Don't worry about what the hexagon means at this point, okay? It will make sense later on. The hexagon is just part of the molecules. What's important is to know that there is an OH here and then there is another OH here. And so, if I have two monomers and I want to join them together, the chemical process to do that is called dehydration synthesis or condensation reaction. Right? Those terms can be used interchangeably. What that means is we are going to be removing OH from one of the molecules and we're going to be removing H from the other one. So if you take H and OH and you put it together, you get the water molecule. But at the same time, we're able to connect these two parts together and form a bond. Okay, so this bond is a covalent bond. It's sharing of electron. So this is called condensation reaction or dehydration synthesis because we are removing a water molecule, right? We're dehydrating the molecules essentially. So that's how you connect monomers together to get polymers. We can do this backwards. If there is a polymer that we want to break apart, then we will add a water molecule. By adding the water molecule, you recreate the individual OH and you separate the two molecules. Okay, so this is called hydrolysis. Hydro is water. You should know that by now. Lysis is to break. We are breaking the bond with water molecule. So to summarize, right, you can have individual monomers like this. Okay? These are monomers. Building blocks. That's what they are. and you can glue them together. You can connect them together with a covalent bond, make a very long chain. Right? This is called dehydration, synthesis, right? Or condensation, reaction. Because you are removing water molecule, right? So plus water. But if you have a long chain, let's say you ate some proteins and you need to digest it, then you need to add water to it, and then it's going to break it apart. This is called hydrolysis. Oh, the program crashed. Give me a second. Oh, I gotta rewrite that thing. And so this is the polymer. And then to go this way is hydrolysis. Okay. Now I have a question for you. Let's say I have three monomers, and I want to join them together. Right? I want to join them together by dehydration synthesis. How many water molecules are we gonna get from this reaction? Well, to connect these two together, I would have one water molecule coming out, and then to form another bond, two water molecules, like that. Okay. Every time you connect two things together, you need to remove a water molecule. What if we have 10 of these things? Okay. And then we're gonna connect them together. How many water molecules in this case?
9.
That's right, Maria. Thank you. 9 H2O. Okay. You need to have 9 bonds. Each bond is one water molecule. So that's it. Okay.
Excuse me, Professor. Sorry, I didn't understand why 9H2O.
Sure, let's draw it out, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So you gotta
Okay.
form a bond here. One water comes out.
Oh, okay.
Yeah, okay.
Okay, now I got it. Thank you.
Sometimes we just have to see it, right?
Yeah, okay.
Okay, so that's that. Take a look at this question. There are 2 monomers below this guy and this guy. And again, don't worry about what the hexagon and the pentagon means right now. It will make sense in a bit, I promise. Okay. And we want to connect them together by dehydration synthesis. Which of the following would be the product? Okay, go ahead. Okay, anyone else? Last call? The correct answer is the most popular one. It is going to be B right here. Okay. So we take away a hydrogen, we take away OH, so that makes H2O, right? And then we're going to connect them together, right? So it's basically the hexagon connected to an O and then connected to the pentagon. This is the answer.
I have a question.
Yes?
Okay, so I think you're saying dehydration synthesis, because I understand dehydration to mean removing water, right?
Yep, absolutely.
Okay, now so in these pictures, after removing the two hydrogens and then one oxygen, so are we like linking after removing, are we just linking to the other oxygen left? Is that what
That's
we're
right,
doing?
exactly.
Okay.
Yeah,
Okay. Got it.
very good. Nicely summarized there.
Okay,
Okay, so
excuse me, Professor, what about C and D? C and D is the same B.
yeah, no, it's not, right? If you take a closer look, these are pentagon and pentagon. That's a hexagon and a hexagon, right? So if you want to drawing a hexagon and a pentagon together, is this
Okay.
one, right? Yeah,
Okay,
a
okay.
little bit tricky. Yeah. All right. Okay. Sorry, there's a student who wants to join the class. Okay, let me just quick yeah, let me just quickly send her the link so she will not miss the thing here. And then we'll continue, okay? Will anybody have the class link here? Class link. Let me see. It's this one, right? Okay, hold on. Give me 1 second. Okay. Sorry about that. Let's keep going. All right. So now we're gonna talk about carbohydrates. Okay, the first macromolecules of the first of the four macromolecules. When I go through these macromolecules, I want you to pay attention to what kind of atom it contains. I want you to pay attention to its normal functions as well as the structure. Okay, we'll summarize all these later on at another time. Yeah, but try to write these things down as we go through it. So let's talk about carbohydrates, which are organic molecules. And again, nothing special about organic. It just means it contains carbon. But in addition to carbon, it also has hydrogen and oxygen. Remember, there are 5 elements that makes up 96% of the body. Well, 3 of them makes up carbohydrates, C, H, and O. The reason they are called carbohydrate is because of the general formula. Okay, C is always going to have the same ratio as the water. For example, if N equals to 6, the formula is C6, H2O, and 6. For carbohydrates, you always have the same part of carbon as water in them. Okay. Now, if I expand the 6 like we do in math class, then it will be C6H12O6, which is the formula for glucose. That's something you have to know in the course. Okay, glucose is the main fuel for our cells. Okay? So that is the carbohydrate. Okay.
Glucose is the what for our cells?
The fuel. Yeah, the
Fuel.
fuel.
Okay,
Yeah.
got it.
Fuel for cells. Yeah. I also enabled caption. Okay, sometimes it's difficult to hear over the mic, or sometimes it's my accent. But turn on the caption. Okay, then you can follow along. Now, like I said, carbohydrates function for quick, short-term cellular energy. You burn them really quickly, and that gives you like a burst of energy. But carbohydrates can also form structural components in plants. If you think about eating fibers in the plants, the crunchy part of a celery stick, the crunchy carrots and whatnot, all these crunchy parts, they are also made up of carbohydrates. But those are not the same kind of carbohydrates that we can burn for fuel. Okay? As you will see, there are different types that exist. Carbohydrates can also form shells of many organisms that have a shell. Okay, like clams, lobster, shrimp, the hard shells. It's also made up of a form of carbohydrates. And again, that's not something we can eat and digest and get energy out of it. But it's important to understand, different organisms use carbohydrates for different purposes. The chemical reaction that describes how glucose is being used as a fuel is written here. Right? So the glucose we get from our food and the oxygen we get from breathing. And afterwards, your body will convert them into carbon dioxide, which we breathe out, water, which we pee out, and most importantly, energy. We will spend the whole lecture 5 talking about this reaction. But for now, I just want to show you that's how your cells make energy. Okay? Your brain is burning glucose as we speak right now to, try to understand what the teacher is saying, right? Okay? If you move your muscle, right, you need to burn glucose to produce energy. So where can we get carbohydrates? And there are different forms. Okay, and there's no shortage of carbohydrates in a diet. It is very, very common. So starch is a type of carbohydrates. We can get it from rice, corn, wheat, potato, right? When you eat pasta, when you eat like starchy stuff like yam, cassava, all these things are very, very rich in carbohydrates, in starch. We can also get carbohydrates in the form of fructose, as the name implies. Fructose is found in fruits. You can also find them in corn syrup, which is an ingredient in a lot of like candy bars and stuff like that. Lactose is found in dairy products like milk, yogurt, cheese, and then sucrose, that's just like kitchen sugar. The kind of sugar in your cabinet, if it's white, it is sucrose. Okay? You find them in candy bars, right? So if you think about your lunch, okay, if you had lunch already, right? Think about where did you get your carbs from? Right? Did you eat a sandwich? If you did, the carbs probably came from the bread, right? Now, let's think about the overall theme of carbohydrates. Right? Carbohydrates, the overall theme of macromolecules, rather. Okay? Macromolecules are made up of building blocks, which we call monomers, right? The little circles that I drew, right? So different macromolecules have different monomers. The building blocks or the monomers for carbohydrates are listed here. Glucose, we saw already, fructose, and galactose. So you would want to remember these things. These are the building blocks, the monomers of carbohydrates. And they are single sugar, right? So we call them mono which means single. Saccharide. Saccharide means sugar. Okay. So that's how you draw glucose. I am never going to ask you to draw them. I'm never going to ask you to identify them on a test or something like that. But you have to memorize the names, okay? But that's what a glucose looked like. It's a hexagon with a bunch of stuff. So earlier when you saw the hexagon with the OH, that's basically a simplified version of a glucose. Over here we have a fructose, which the chemical shape is a pentagon, and that was what the pentagon was representing. Okay, so glucose, fructose, galactose, these are monosaccharide. They are single sugar. Well, these sugar, they are single and they are ready to mingle. So you can put two of them together to form a disaccharide. A disaccharide. So for example, if you take glucose and you connect it with a fructose. Now don't let all these extra things confuse you. It's all the same. We basically take a hydrogen off from one of them and we take an OH off the other one. So when you remove these things, what do you get in the end? You get H2O, right? And then you make a new connection that joins the monomer together. Okay. So now the product that you get are two sugars connected together. They no longer is considered as monosaccharide, but rather it is disaccharide. Disaccharide, double sugar, right? Okay. Does anybody have any questions so far? All right. Sucrose is the kitchen sugar, right? In case you missed that last time. So there are different combinations we can have. We can have glucose connected with glucose, and that's gonna give you maltose. Look at any candy bars that you might have at home or in your knapsack. If you take a look at the ingredient, I guarantee you're gonna see maltose. Okay? If it does have maltose, it's probably a very healthy candy bar, and I don't want to eat it. It probably tastes gross. Next one, we have glucose and galactose. Right? Glucose and galactose, if you connect the two of them together, you are gonna get lactose. Remind me, where do you find lactose?
Milk.
Yes, milk, right? Dairy stuff, okay? Ice cream, right? If you take glucose and you connect it with fructose, then you will get your kitchen sugar, the sucrose. Okay, so all these things here, those are monosaccharide. Those are the single sugar. Whereas these one over here, these one over here, that's what you get when you join two of them together. And they are the disaccharide. Okay. So I could ask you which of the following is a disaccharide, which of the following is a monosaccharide. You would have to know. So what happens if you connect even more? Right? So two of them, right? But what if I add more? What am I gonna get, right? But before that, I forgot we have a slide here, which is talk about lactose intolerant. Some people cannot digest lactose because they are missing. It's called an enzyme. We'll learn about it next class. But it's a thing that's required in the body to break down lactose. If you don't have that, you cannot break down lactose. And instead, the bacteria, they're gonna like feast on the lactose, and all of those bacterial activity is gonna make you feel gassy. You're gonna feel bloated, and it might make you have diarrhea. Okay, so people who have who are lactose intolerant, if they want to have ice cream or something like that, they can buy this thing, which is the lactase enzyme. So you pop one of these things before you eat your dairy, and the pill will help you digest the sugar. Okay. So we're gonna wrap this up by talking about what happens if you put multiple sugar together to form a very, very long chain. So not just two red circles, so to speak, but a whole chain of them, okay? Once you connect multiple of these things together, we call it polysaccharides. Polysaccharides, very long chain of sugar, right? So they are either straight, okay, straight like that, or they could be branched. So along the main line, you might have like other lines coming out, or sometimes they could be very, very branched, extensively branched. So they could branch out from the branches and kind of form like a tree branch, right? If you would. Okay. So depending on how the branching occurs and how complex it is, then you get complex carbohydrates or simple carbohydrates. You might have heard people say, it's better to eat complex carbohydrates because your body doesn't burn it up as quickly, and therefore it's healthier for you, right? Compared to quick bursts of energy that you might get from simple carbs. All right. So that depends on how many times is being branched, right? Now, I have a few examples of polysaccharides here. The first one is called cellulose, and the next one is glycogen, and then starch. They are all made up of glucose monomers only. Okay. The difference between them is how the glucose are being connected. Okay, and how much branching you have, but they are all made up of just glucose. Okay, so no galactose, no fructose, just glucose alone. So let's start with cellulose. Here's a picture of cellulose. You don't have to memorize it, but it just shows you it's a bunch of glucose, right? Connected in a particular way. And these cellulose strands, they are really strong because they can be braided together, okay, to form like a rope structure. And so they are excellent for forming structure for plants, for other organisms, and it's found in the plant cell wall. Okay, if you don't know what a cell wall is, this is a cell, and outside of the cell, there is like a extra protective layer. Okay, like this. Okay, so that extra protective layer, which we'll learn more in lecture 3, that's the cell wall. We don't have cell walls, okay? Plants, they have cell walls, and that protects them, okay? Makes them extra strong. That stuff is made up of cellulose. We cannot digest cellulose, okay? When we eat fibers, the cellulose stimulate our intestines, and then it helps things move along. So dietary fibers, they are important for good health, but like I said, we cannot extract the nutrients from it. Okay, it just pass through our intestinal tracts. Cows, they of course feed on grass, right, and other animals too, like deers and stuff like that. They have special bacteria in their guts that helps them break down the grass cellulose and extract nutrients from it. Okay, we cannot do it because we don't have those special bacteria. So if we eat grass, it would hurt because it's like mostly fibers with very little usable carbs for us. But think about eating the celery sticks. Okay, all those fibers would just pass through our system, but we're able to digest like the actual food part of it. Now, the other one is starch. Okay? Starch is the storage form of energy in plants. Right? Plants is able to make their own food, right, by using the sun's energy. and they make these extra food and they store them in the stems and the roots, and they could use it in winter's time when there's not a lot of sun. But we can take the stem and the root, and we basically eat the starch that are produced by the plants, and we can take the energy from it. It's also made up of glucose. All these little hexagons, they are glucose. And when we eat them, we basically use hydrolysis to break off a glucose, and then we would burn it in the chemical equation I showed you, right? And then you would break another one, and you break another one. That's how we harness energy from it. Okay, but starch, the um, the normal function is for plants to store their energy. We can also store energy, but the form we store it in is called glycogen. If you look at the structure between glycogen and starch, starch is branched, right? But glycogen is even more branched. We will store the glycogen in muscle as well as liver. Those of you who don't know where the liver is, it is on your right hand side, okay, right here, okay, the liver under your diaphragm. And when we eat more than we need, we will store them as glycogen. If you skip lunch today or skip breakfast and you haven't eaten anything all day long yet, your body is taking the glucose from the liver, from the muscle, right, and breaking it off from the glycogen and using it to help you run until you eat again later. So here we have it. The starch is the storage form of energy in plants, glycogen, storage form of energy in animals, and then the cellulose. It's the structural part of the of plants. Okay, we cannot digest cellulose. You need special bacteria in your gut to digest them, and those are found in cows and deers. And finally, I want to show you one more before we finish this. And it's another kind of carbohydrates called chitin. That's how you pronounce it, not chitin, but chitin. Chitin contains like a modified kind of glucose. It looks like glucose. It has the hexagon, but it also contains nitrogen. Remember, for the regular carbohydrate, it's only C, H, and O, right? Okay, this one has a little bit of nitrogen in it as well. And chitin is important for forming the shells of the exoskeleton, right? The shells of crabs, lobsters, as well as insects. Okay, these animals have exoskeleton because the hard part is on the outside. Humans, we have endoskeleton, right? Our bones are inside our body, right? So that hard part is made up of chitin. Okay? Chitin can also be made into surgical threads, which is wonderful because it's biodegradable. So when you stitch a person up using chitin, you don't have to go back and remove the stitches. It just, melts on its own, and it allows the wound to heal a little bit better. If you had removed your wisdom teeth, they probably stitch you up with chitin, okay? And it just dissolves in your mouth, right? So there you have it, the different kinds of carbohydrates. Now I'm just going to take up these questions with you, okay? And then we'll be done. Sucrose, which is a disaccharide, is made up of which of the following sugars? All you have to do is look it up, right, from the slides. And hopefully you remember sucrose is glucose and fructose. Okay. And here is the last question. That would be an example of a multi-select question. Remember, on the quiz or test, some questions will have more than one correct answers, and you have to choose all the correct ones, right? Those questions will specify, choose all correct answers in them, so you know. Right? So let's take a look at this one. First, Polysaccharides are important both for energy storage and to provide structure to cells. That is correct. Okay, energy storage example would be starch and glycogen. For structure, example would be cellulose and the new one we learned, right? The chitin. Right? So that's a correct statement. We are looking for the false one. Glycogen is important both for energy storage and to provide structure for cells. That is not true. It does not provide structure for cells. Okay, only energy storage. Cellulose is only found in animals. That is not true. Cellulose are only found in plants, right? Glucose, fructose, and galactose are examples of monosaccharides. That's correct. If you look at the list, right? The single sugar, right? That's what they are. Starch is a storage polysaccharide made by plant cells. That is correct. Storage form of energy in plants. Right? So the only answers that are incorrect would be B and C. Okay, that's it for today. Please start studying for the quiz, which is going to be happening. Let me see. I believe it's next week. What are you guys online? Yeah, it's going to be next Wednesday. Okay, and it's going to be all of lecture 1 and lecture 2. So start studying today. Okay, the answers to the study guides are available, right, for lecture 1. So please go through those as well. That's all. Thank you for coming.
Is the quiz for this coming Wednesday?
Next Wednesday, 24th.
20,
Next
okay.
Wednesday. Yeah. Okay. And I'll post information about it later. Okay. Is it going to be open? Yeah, the quiz is going to be available from 6 a.m. to 11:59 p.m. Okay. So not the whole day, but pretty big window. Right. You can do it anytime during that day. And we still have class on that day, right? You still have to come for the our regular session.
Professor, how many questions?
I honestly don't remember on top of my head, but I will post the information. Okay.
Okay. Okay.
Probably like either today or on Wednesday. Right?
Okay. Thank you.
Any other questions? Okay. Well, have a good day, guys. Stay warm. Bye for now.
I had something to say.
Yeah, sure. Go ahead.
It's